You have to get above the atmosphere to have a look at. And being able to observe in UV and ultra infrared wave bands is important because it can penetrate dust and dust clouds better than visible light, and it's good for identifying exoplanets, young stars, and doing chemical analysis. This is a Hubble image of something or other taken with visible light, and then they fitted an infrared capability to Hubble, had another go, and this is what came out of it. Less pretty, but a huge amount more data. You can see all these stars and so on, which were not visible because of the dust and gas in the original image. Early universe. Sorry about this, but we're going to go through it. After about 20 minutes, the universe was filled with protons, a few neutrons, and electrons. And they were all whizzing around at very high speed, and the electrons were dissociated from the protons. There was also a lot of dark matter, and 84% of the mass of the universe is this dark matter. So all the stars and galaxies you see count for virtually nothing in terms of the mass. And there's energy. Einstein said, empty space is not nothing. But this plasma was expanding and cooling at a prodigious rate in the early universe. And it gets to a stage after 380,000 years, the electrons were moving slowly enough to be captured by the protons. So now we have atoms of gas. That process meant it had to release energy. And so just about every atom in the universe emitted a photon, just to say it's joined up with his friend. Now we have hot gas, but the gas is opaque because a gas atom or molecule takes up a lot more space, or has a larger cross-section, as they say, than the individual components. So it was opaque and there were no bright objects. So that was now the start of the universe dark ages. It was dark, no form, nothing. What about dark matter? Well, that got spewed out at the beginning of the universe in what they call the cosmic web. I like to call it the cosmic sneeze, really, because it's got these strings and blobs of material. And the only thing we know about dark matter is that it gravitates. It's got mass, and so it gravitates. Doesn't interact with anything, but things are attracted to it. And the gas in the universe was attracted to these blobs and strings, rather like, if you go for an early morning walk, you see a spider's web, you see the dew has been attracted to these areas where you get these strings and blobs. And you might get individual galaxies along the strings, but you get galaxy clusters growing in the blobs. That's enough of that. So these blobs will seed the galaxies and galaxy clusters that we're more or less seeing today. After 100 million years, the first stars are starting to form. Now, in these gravitational areas where we've collected some gas, and gas is coming together, you get some localized spots where you get even more gravity, slightly denser gas that acts as a magnet for other gas that's in there, and so that all starts to accumulate towards these individual areas into clumps. Now, you've done your thermodynamics. These clumps will be condensing, increasing in pressure, therefore increasing in temperature. So what happens? What's going to stop this process going on? Well, at 17 million kelvins, hydrogen starts fusing to helium. And the amount of radiation that comes from the fusion process is enough to stop the star collapsing on itself. These stars are huge, hot, very bright, until they run out of fuel, i.e. run out of hydrogen. There's no more to fuse. And so the whole thing collapses. Imagine the sun, a star collapsing in on itself, massive amount of energy, you get a supernova. The conditions in that supernova are so violent that they throw the atoms together and produce just about every element in the periodic table. That's where these elements have come from. The elements that are heavier than helium are called dust. And that's one of the problems we have with telescopes. A billion years later, the next generation of stars start to form, and now they've got dust stuff to work on, and so we get planets coming out of the star formation process. Also, galaxies are starting to interact and cluster and play with themselves. So that was the early universe on one slide. Hope so, right? So what was the vision? The vision came out in 1996. They wanted the next generation of space telescope for visiting a time when galaxies were young. What do we mean by that? Well, in the 1990s, before Hubble, the best telescopes we had could see things that were 6 billion, produced when the universe was 6 billion years old. That's nearly half its current age. Hubble got up there with its deep field and it went back to 1.5 billion years old. A couple of upgrades later, it was getting back to just about 500 million years. Unfortunately, the exciting things happened before that time, and so the James Webb is meant to go back to about 200 million years after the Big Bang. That's as far back as you're going to go, because before that, it's Dark Ages. So its mission is to observe the earliest visual events of the universe and to study its development to its present form. So its key questions: what is the shape of the universe? That might not seem as silly as it sounds, because what happened in the 1920s, we're about here, Edwin Hubble was looking at galaxies and he noticed there was a correlation between the speed with which they were moving away from us and the distance from us. And that implied you could go back and the universe had a beginning and it was going to expand forever. Or was it? That was the trajectory we were on, but we've got gravity. So that was going to slow down the expansion, but it could still carry on expanding forever. At some critical density, the universe would have an asymptotic expansion rate, so it could become flat. It get to a certain size and not grow any larger or smaller, but that's a very delicate position. The other one is an even more dense universe. You have what's called a closed universe, which is where the universe gets to a certain size, gravity takes over and it pulls it all back together into a big crunch. Big question, which one is it? Well, in the late 90s, they had a good look at this. And to their horror, they found the universe was accelerating. There's some force opposing gravity, expanding the universe at an exponential rate. What is this force? It's called dark energy. That's all we know about it. Another question, what is the shape of, what is the shape of the universe? How do these galaxies evolve? Now we know that you get some material and it spins up into a disk and there's a large central bulge in the middle. But what about these arms? And what about these pretty well mirror image disks, areas in the disk, which are star forming areas? What's all that about? And what about the black hole in the middle? How big does that have to be to start? And our planetary system, these are our planets, fairly eclectic mix, but why are they where they are? And how did they form? Why are the rocky planets on the inside not further out like Pluto and so on? And how did the elemental composition arise? Well, we know sort of about that. What is the nature of dark matter? Yep. And are there any clues regarding dark energy? So some massive questions there that poor James Webb has been told to have a look at. And of course, is there evidence of life in the universe outside the Earth? So that was the concept. It's got to be launchable. It's got to be sensitive. It needs to be able to detect a small galaxy 300 million years after the Big Bang. And that is like looking at the heat signature of a bumblebee on the moon. Don't think too hard about the mechanics of that, but you get the idea. The aperture, the size of the mirror, they wanted 8 meters diameter, but they accepted reluctantly 6.5 meters. But in order to be able to do what it needed to do, it had to have unsurpassed stability and pointing accuracy. It had to point extremely accurately and be able to hold that position for hours. It needed to look at the near to infrared to the mid-infrared wavelengths. Visible light and ultraviolet was no good. To get the detectors to operate, they had to be very cold. So we had to be very careful about heat management on the telescope. And it had to have a resolving power better than 0.1 arc seconds. That is like being able to resolve the full stop on a newspaper page at 1,000 meters. Its instruments wouldn't just be a camera for making pictures. Spectrographs were very important, and also coronagraphs. And the operating life had to be in excess of 5 years. It needed 5 years to do what was known as the design reference mission, which is all the stuff that the astronomers decided it needed to do before they knew what it could do. And it wasn't going to be serviceable. See, with the Hubble, they could fix it. This thing, they can't. So let's start putting this into reality. The launch system. The Hubble was, the space shuttle was out of commission, or going out of commission. The only real contender was the Ariane 5. European Space Agency, that was their major contribution to this endeavour, was the launch. The primary mirror, pretty big. This is to scale with the Hubble, and it was segmented so it could be folded. Heat management, two ways of doing that. One is where you put it, the other one is shielding it. And this is a model in 2005 of what it would look like. It doesn't actually work at that stage. Image quality, how is it going to get this resolution? Well, very careful design. Top opticians were working on this project. Precision build, time and time again, they had to check things and invent new ways of measuring things so they could make sure it was built to the right precision. It was going to have adjustable optics. So when things drift off a bit, as they do over time, could be able to put it right. And very rigorous testing. The testing regime was second to none because they'd learned their lesson from Hubble, because that went wrong. So let's build our telescope. First of all, we have what's called the optical telescope element. Light comes in from our object across the whole width of the mirror, and every photon that hits the mirror goes onto the secondary mirror, which is reflected onto the tertiary mirror, which then gets onto the fine steering mirror and ends up on the telescope focal plane. And that's where the instruments start picking up their image. We need the instruments on the back, and they're strapped to the back plane. Then there's a deployable tower to separate the spacecraft bus, which generates heat because of the electronics and everything else, from the very sensitive instruments in the ISIM. And then we stick a sun shield around there to protect the optics and the instruments from the radiation that will come in from the bottom. Let's have a look at that. The Earth is 93 million miles from the sun, and so it goes round in an orbit roughly 365 days long. There's the Earth, there's the Moon, and there's the sun, all generating heat. That's what we want to get rid of. It seems like a good idea to always try and be in line with all of these radiation points, so then you've got an easier shielding project. So there's the telescope, and there's its shielding the sensitive bits from the sun. Unfortunately, if you go up 1 million miles away, we're on a 371-day orbit. But the cunning bit is that if all these are in line, the combined effect of the Earth, Moon and Sun give you a 365-day orbit. So this will stay in step with the Earth as it goes round. That is called the Lagrange L2 point. And just to stabilise things, it goes on a lazy orbit as it rolls around alongside the Earth. Let's build our telescope. There's a spacecraft bus, just the chassis of the instrument. It's got all the other stuff that you would expect, communications and so on. The sun shield. Yeah, you can get one of these in B&Q, can't you? It's pretty big. It's got to be 20 meters by 14 meters, which is about the size of a tennis court. It's made of 5 layers of Kapton film. Kapton was a material developed in the 1950s by DuPont. But the important thing is how much it's doing. We've got to accept 300 kilowatts of energy on the underside and emit only 23 milliwatts on the other side. That's an attenuation of 1 to 10 billion. I've gone off. No, again. Is the splitting of these layers because they need to reflect the energy out into space. They can't afford to allow any of this energy to build up. In order to see how this was going to work in this environment, because the whole thing was untestable, they had to develop a new set of finite element analysis techniques. This sun shield has got 140 release mechanisms, 70 hinge assemblies, 8 deployment motors, 400 pulleys, and 90 cables. Everything has got to work. What could go wrong? Now then, the primary mirror, another biggie. It had to be folded to fit the Ariane 5. You can see this is the main mirror here. That's one wing unfolded. That's the other one folded in. You get some idea of the size of it by these people down here. So there it is, neatly tucked into the cargo bay of the Ariane 5. These 18 segments have 3 separate complex prescriptions. They're not spherical or anything simple like that. They are very carefully designed to make sure that every photon that hits that mirror anywhere from an object will go down a single point on the instruments inside. It had to be much lighter than the Hubble mirror, which was made of glass. Effective focal length of 130 meters. Takes a bit of pointing, doesn't it? What are they going to make it from? Well, glass was not on because it's too heavy. They tried beryllium, they built and tested one of each, and they found they could build one. Beryllium has got various good properties. It's lightweight, very strong, low coefficient of thermal expansion. In fact, it's stable at cryogenic temperatures, so a small change of temperature doesn't alter its shape or size. Good conductor of heat and electricity, and not magnetic. Unfortunately, it's a bit toxic in powder form and difficult to polish. Ho-hum. Now, they made these things by, first of all, taking beryllium powder and mixing it thoroughly to make sure there are no inhomogeneities within the parcel, and then compressed to form a solid material. Then they machined most of it away. It was ground, polished, cooled down to operating temperature, and the distortion measured. Hey ho, we've got a bit of a valley in there, pardon me. So it was brought back to ambient and the shape correction applied. They gave it a final polish, and then they coated it with gold and then glass. Why gold? Well, gold has got much better reflectance at the longer wavelengths than many other materials. And that's why gold is the colour that it is. And then it was cooled and checked again, and hey ho, we got a decent mirror. So that was a segment. They made 7 of each prescription. In case they dropped one, that would have been bad luck. The backplane, quite simple really. It's the spine of the telescope, carries quite a lot of hardware. These are the 2 wings, you can see, and it's made of carbon fibre, and everything's a box beam truss design. In other words, there are no bending moments in there at all. It's all compression and tension. We needed 10 nanometers of stability, so it had to be pretty well made. And the actual making of it in space or deploying, it's got 2 hinges on each wing and 3 latches. 2 wings are these blue bits, and we've got 3 latches, 1, 2, 3. To open the wings, you have a stepper motor operating on the hinge pin. On the latches, you have motorized bolts, and you have a fixture down here to make sure that it doesn't over constrain. And these are the latches that it latches into. You have a ball and conical valley will be the first one. So the wing can come out and then swing about on that one. The second one is down the bottom, and that's a cone and valley, or cone and groove, and that stops it swinging about. And the third one just locks it in place. So those 3 constraints fix the wing. And they're so accurately positioned that the hinges are no longer in the load path. So they know exactly what loads there are on the backplane. Mounting the mirrors, segments, transportation, launch and deployment loads, ultra precise adjustments through life. It's The mounting is based on a hexapod mount, which has got 6 actuators. They can all be independently extended or contracted, and that gives us several degrees of freedom. You've got tipping, tilting, sideways, translating, blocking, which is spinning, and piston. So these, if they're carefully controlled, can give you all those movements you need. Those are the Webb bipods, and that's the actuator bit through there. I'll go into that in a moment. These actuators, they need 10 nanometers precision with 20 millimeters of travel. Out of its holding position and then move it around to the other segments. The fine stage comprises a frame with an eccentric bearing. If this goes up, it pulls the ends of this beam in a bit. If this comes in a bit, this goes up an even smaller bit. So that is the fine movement. It's achieved with a stepping motor through a gear ratio and then a cam. So that can go round and round, and this goes up and down, but you only want it to go up or down. The repeatability of this is jaw-dropping as far as I'm concerned. It's repeatable to 1 nanometer. Remember I said I couldn't understand what it was? 2/100th of a thousandth of a human hair. No hysteresis, no backlash, and repeatable with the 7 nanometer step, which gives us our 10 nanometer precision requirement. So it exceeds the requirement there. Then the course drive, we add a bit more gubbinry to this drive here, another gear ratio here. And then this is what's called a tumbler coupling, which means this bit can operate nearly a full circle before it engages with this. This drives for another couple of gears and then a precision screw. And that's got a pitch, a fine pitch, goes through 21 millimeters of range. So it's now got the 20 millimeters of travel. Aren't these good? 7 segments, 7 actuators per segment. You've got the 6 in the hexapod mounting. They go on here, but there's one central one going through these struts that can adjust the curvature of the mirror should that be necessary. It's thought highly unlikely, but there it is. How do they know whether it's flat or not, or probably in focus? Yeah, okay, sorry about that. We're now pointing. The attitude control system provides course pointing and roll control. This gives pointing to less than 8 arc seconds, which is like a credit card at 1,000 meters. 6 gyroscopes. The gyroscopes have always been the Achilles heel of space telescopes because they can't stop the bearings from failing. This one doesn't use any bearings. It uses a finely ground hemispherical lump of quartz on which they set up a standing wave, and that acts as the gyroscopic element. Reaction wheels, yes, you need those to turn the telescope. It's got thrusters to help the reaction wheels and star trackers to control the roll of the telescope, because it's all very well pointing the telescope at something, but you've got to stop it from rolling. And then on top of that, you've got the fine guidance system, which provides the fine pointing. The fine guidance system acquires a guide star in the telescope field of view, and you know how far away from a guide star the object of interest is, and so you move the telescope onto the object, and then the system will keep the guide star in that position. And it maintains pointing to less than 10 milliarc seconds, so it's got a precision of half the diameter of a human hair at 1,000 meters, and it can hold it there for an indefinite period. Right, the instruments have got a camera, near-infrared spectrographs, near-infrared imager and slitless spectrograph, and the mid-infrared instrument. That's what they call it. They're all held in the Integrated Science Instrument module, which is attached to the back of the backplane. And the camera, that gives you, as a basic imaging instrument, that gives you pretty pictures, large field of view, identifies things for people to be interested in, stores all this information in a huge database down on Earth. so that it can be looked at in time future by astronomers looking for something specific. It doesn't do things in color. It's a black and white image, but it goes through different filters to broadband, medium band, narrow band filters to give you the colors you need. And they are held in these filter wheel assemblies which click round and are put into the optical path of the telescope at the right position. Quick refresher on spectrography. If you've got a source of light, you pass it through a disperser and it splits it into colors, and so the image you get is a streak rather than a dot. So if you've got a slitless spectroscopy, you've got a star field there to study, you have a whole load of these streaks. If it's a busy star field, you put a slit mask on so you can mask out all the rubbish and just concentrate on one object. The spectrum has spectral lines in it, which are absorbed by different chemicals in the optical path. These can be shifted, and one type is called the Doppler shift, which you're all familiar with. It's a high note as it comes towards you, a lower note when it goes past, but also cosmic shift. The universe has been expanding, and so these wavelengths have been lengthened. And that's why the early stuff in the universe needs to be looked at in infrared. Now, these spectra give all sorts of things like chemistry, temperature, mass, velocity, age of the object, activity, and all sorts of things. So this is where the data comes in that gives the birth to these scientific papers. Going on from the spectrograph, we've got the integrated field unit or integral field unit. If we've got a large object that you want to look at, you can split it up into various bits and pieces by looking at it through a special mirror, which has got different facets on it. And so the object is split up and you throw the whole scene at your imager, got a disperser, and then you get different spectra for different parts of the object. The Webb's imager has got 900 mirror facets on it, 30 by 30. And that will produce a spectra like this, which gives a whole new meaning to what must be in there. So this is the workhorse of spectral analysis. Coronagraph, you're all familiar with looking at the moon when it's in front of the sun. You can see the sun's atmosphere behind. Bernard Leo had a go at making a telescope that had a mask and a stop. The mask blots out the sun and the stop blots out the surrounding stray light. And you end up with only about 2% of the original starlight in there, although you can see the object to the side of it reasonably clearly. But we can go better than that. The technique called aperture masking interferometry. If you have two sources of the same image and overlap them, they will interfere. And with clever computer analysis, you can work out quite a lot about those two separate images. This would be the normal view of binary star and a single star. Going through the aperture masking process, you get a lot more information, and the analysis and the astronomers think that that's really good. Well, it is actually, because we can now detect and characterize a 9 magnitude fainter comparison at 100 milliarc seconds. That's equivalent to saying two pinpricks, 0.5 millimeter apart, 1,000 meters away, with a 1,000,000,000 to 1 contrast ratio, and you can detect and analyze the fainter of those two objects. Yeah, that's good, isn't it? We've got aberration-free light paths. That's the problem with any telescope, is aberration. For every change of direction, yeah, let's just whiz through the instruments. There's 4 of these. Near infrared, we've got 3 of them. The near infrared camera. The functionality of the device depends on what you put in the light path, all these filters and masks and what have you. And that images onto a 16 megapixel array. Wavefront sensing, which will help identify the irregularities in the optics, an imager, which is a camera, and spectrography. And also the shorter wavelength sensing, again, imager and coronagraphy. Module B is exactly the same as Module A, because wavefront sensing is so important to the functioning of the telescope that you've got 100% redundancy. And there it is, Module A, Module B underneath it. The spectrograph, much larger field of view, filter wheel, compound mask unit, that's a bit interesting, can do single object, integral field unit, and multi-object. How does it look at multiple objects at the same time? Well, I'll go on to that in a moment. And the imager and slitless spectrographer, very similar, broadband imaging, wide field slitless, and single object slitless using a prism. That's only a 4 megapixel camera, but it also does the coronography. Within NIRISS is housed the fine guidance system, which is just an average size field of view and looking at the guide star, which it holds in position on the detector. And that is also so important to the functioning of the telescope that it's duplicated. So another lot of 100% redundancy. And there we are. Now, looking at these dense fields in the spectrographer, say you are interested in that galaxy there, you want to take a spectrograph of it. You might want to stare at it for about 10 minutes or even 10 hours to get what you need. So to keep everything neat and tidy, you put your mask up there with a slit, and that allows you to take your observation. But at the same time, you might also be interested in this object here. Wouldn't it be good if you had a slit also over that object? Well, you can. We have this array of these little shutters. When I say little, those human hairs on roughly the same scale. And you've got 250,000 of these, all independently programmable and latchable into the open or closed position. So you can look at any star field and select what you want to look at. And the maximum you can have is about 100 shutters open. And that's the sort of image you get. Again, this is all stored away for later consumption by interested parties. And there it is. It's just about 3.5 inches, 3.5 inches square. Now, the mid-infrared instrument, this is the beast of them all. Very compound mask, lots of filters, does imaging and spectroscopy. It's only got a 1 megapixel camera, by the way, on here. And then it takes a very small field of view, puts it through filters and dichroics and dispersers, then into the integral field units. There's one for each channel, different colors, different wavelengths. The detail of all of this is beyond my comprehension. It's extremely important to get this right, apparently, and the astronomers are overwhelmed and overjoyed with the quality of it all, because it gives them so much information. Here you can see it mounted on these thermal struts, because the whole thing has got to be kept at a very cold temperature. The instrument itself has got to be kept at 18 Kelvin, and the detectors have got to be kept at 6.2 Kelvin, which is as near absolute zero as you can imagine. So we built the telescope, we chuck it on a ship, we trundle down the coast here, through the Panama Canal, round to British Columbia. British Columbia, I beg your pardon, French Guiana. It's much nearer to the equator, and so you get a good equatorial speed assistance. And off it goes. This happened on Christmas Day 2021. It was a real nail biter. It was broadcast live over the net, and I must say I did stay up and watch it. There's enormous amount of vibration on the end of this rocket, and it's shaking the stuff to bits at the top. Must be heartbreaking for the people that put so much precision into building what they built. What have they got to do? Well, I don't know if you play golf, but here we are. One of the trickiest golf shots in history. You have to whack the ball, and it happened at 7:20 in the morning. Whack. And then it's got a free float up to this point here, and it mustn't go over the top. If you hit it too slowly, you can always give it a boost, but you're going to use fuel, and fuel is important for the life of the telescope. And it's coasting for 26 days, and the boost only lasts for 27 minutes. So it's in free flight most of the time. So really exciting period, and you could hear the commentator getting more excited as he went on. And finally, it was released from the third stage of the rocket on springs, just a gentle push away. And it was heard the commentators say, "Go Webb, do your thing." Well, it did. We had a few issues. The sun shield deployment didn't work very well because there was no signal coming from the cover sensor to say that it had been rolled back. But the guy on the temperatures said, well, it must be all right because it's you wouldn't get those temperatures if the sun shield was there. You might remember a micrometeorite hit it quite soon in its life, caused some damage. It was expected to have some hits, but this one was unusually high. But the optical performance is still twice as good as the requirements. So that goes something to say how well it was built in the first place. And now what they're going to do is when they know there's a threat, they're going to turn the telescope sideways so that it minimizes the impact area. And one of the grating wheels had some friction on it, which was unaccounted for, and they've worked out how to get around that. And there's a further problem with MIRI is that one of the filters is not transmitting the light as well as it should, but they can compensate for that. Finding so far, I mean, I could go on forever with this because it's finding something pretty well every day. But this is one of the first images. It's a sharpness check. And this brought gasps of surprise and actually tears in the audience when they saw how sharp these images were. This was the best they had before with the Spitzer telescope. And this is Webb. You see all the massive amount of detail compared to what's in the Spitzer image. You might have seen this iconic image of Hubble called the Pillars of Creation. It was then retaken with the wide field camera in Hubble in 2009. Wide field means it can capture more, but still pretty flaky in terms of what goes on inside these dust clouds and so on. Along came Webb. This is near infrared camera, and then the infrared camera, mid-infrared camera, even more detail, and they've got some stuff here on the gases and so on. So it really has changed the way things are looked at in space. This is one of the spectacular images. It doesn't actually tell you a great deal, but there's a star, powerful star, a long way north of here. And it's hosing these dust clouds and molecular clouds with high radiation. And so it's ionizing the information and it's like clearing it out. So that's what happened in the early universe, is this ionizing radiation made it transparent. It's looking at the composition of Mars, its atmosphere. It's found water and carbon dioxide, as you would expect. It's even seen the surface features of Mars all the way from Earth. Looking at Jupiter is showing all sorts of stuff here that you could only see when you sent a mission to it in the first place. Well, this is not from a mission, this is from the Earth. So Saturn's got a moon called Titan, and you could even see the weather changing from the 4th of November to the 6th of November, these clouds and so on forming over the moon. Enceladus is one of Saturn's moons. It's got an icy surface, unmarked by craters, so that gives it an interesting opposite position. What they found, what they've seen on Cassini, which was a probe that was sent there, were these little plumes of water vapor coming out of the planet. What Webb has shown is that there is the thing on the same scale. It's got this massive plume of water vapor, and this water vapor is feeding the moon system of Saturn. Uranus, even further out, sorry, Neptune, beg pardon, you can see the clouds, and also it's got a ring system. How interesting is that? It looked at the main belt comet as a comet in the main asteroid belt. One of the questions we have is, where did all the Earth's water come from? Because during its formation, it was too hot to have any water on it. It would all evaporated. So it's come from somewhere. And the proposal was it's come from comets and asteroids that hit the Earth. And we've now got this breakthrough discovery that it definitely could have survived from the early solar system. So when the water was formed in the early solar system, it survived in the form of attachments to comets and asteroids. And this is the emission spectrum. No carbon dioxide on this one, but there is some on there, and water on both of them. There's an exoplanet called WASP 96b. What happens when the planet goes in front of the star, the brightness of the star dips for a little bit and then it goes up again. That's how they discover some exoplanets. But they are able to manage to take a spectrum of this, and it's got lots of water vapor. And it also showed hazes. Which is never there. Anyway, the haze in the atmosphere is glass, like molten glass droplets. This is a direct image of a planet, an exoplanet. Never mind the bars, they are artifacts. But this is NIRCam taking these two and MIRI taking these two of the same planet. So we're now getting images of these distant planets that were just a figment of the imagination not that many years ago. This exoplanet, more massive than the Earth. It's got methane and carbon dioxide, but a shortage of ammonia suggests that there's a water ocean beneath a hydrogen-rich atmosphere. Also, possible detection of dimethyl sulfide. Sounds like something out of Star Trek, doesn't it? But anyway, almost all of dimethyl sulfide on Earth is from marine phytoplankton. So it implies that there could be life producing this dimethyl sulfide. Still needs further look. These are two galaxies interacting. It was exciting enough to want to show President Macron and Vice President Harris in November 22. Deep sky observations require some special techniques. You have this thing called cosmic redshift. I've briefly mentioned that. The popular view is if you've got space represented by this grid and the universe represented by that the universe is expanding like that into space. Wrong. The universe contains everything, including space and time. So what happens is the whole lot expands. So if you had some photons in the early universe, by the time those photons reach us, they've been stretched. And that's why we're looking at what used to be visible light radiation from the very early beginnings. We're looking at it now in mid-infrared. We also have dark matter. What can I say about dark matter? Well, just a few words. No interaction at all with ordinary matter. So there's no way we can touch it, feel it, measure it, anything. You can't even heat it up because you can't measure its temperature. It does have mass, so it gravitates. And there's 5 times as much dark matter as there is ordinary matter in the universe. And it's the force, well, it's the stuff, the gravitational force holds galaxies and clusters together. Otherwise, they just couldn't rotate at the speed they do. And we can map it by the gravitational lensing that it produces. I'll just go on to gravitational lensing. Imagine you're wanting to look at something over there and there's something gets in the way. What we see is an image of what we're looking at, but something gets in the way, and so we no longer see it. We can see this cluster or whatever here of dark matter. But light can travel close to it, and according to Einstein, because it's massless, it can still be bent by gravity. So what we see is an image of this, some displacement. So we've got an image like that. And you could also get another ray coming down underneath. So you get a splurge like that. So this is called gravitational lensing. So Webb had a look at a deep field, looked at a cluster that was 4 billion light years away. So about a third of the way back to where the beginning of the universe was. 12.5-hour exposure. And what we can see is lots of lensing going on here of these galaxies that are 13 billion light years away, near the beginning of time. So this is how we can get a view of some of these very distant galaxies. And it's sufficient to get a spectrograph of the object that we were expecting to see. And oxygen, hydrogen predominate, a little bit of neon, which is what you'd expect. And that little fella, you can't see it. And the final one I want to talk about is dark stars, or more, I call them dark matter stars. Stars are driven by dark matter self-annihilation. Because dark matter particles don't have any electrical charge, they don't repel each other like protons do. If they happen to go towards each other, they will collide. Now, it's like shooting moths in a hangar. It would be a very rare occasion. But when the universe was dense enough, you could have this dark matter self-annihilation going on at a steady rate. You only need a little bit of it in amongst the early protostars, 0.1%. And the intense radiation from this dark matter annihilation will prevent the star from collapsing. So there's no reason why this star shouldn't just grow and grow and grow. It could be more than 1 million times the mass of the sun. Before it runs out of dark matter, then it just becomes a huge ordinary matter star. So it collapses, heats up, core reaches 100 million Kelvin, fusion begins. And eventually that will run out of hydrogen fusion and collapse into a very large black hole. Do these black holes seed the supermassive black holes we observe today at the beginning of all galaxies? Watch this space. It's all got to be looked at still. That was conjecture, but now, last week or last month, the Webb discovered 3 such galaxies that are strong contenders for these dark matter star seeds. So, yes, go Webb. You are doing your thing. Thank you. Yes.
That's another lecture at some point.
Yep.
But I'd like to thank you for coming and talking to us tonight. It's been really interesting. We've had some good questions and discussion, and all our lecturers get our famous gift of our golden crystal. That's like to present to you, because we do represent,
Oh, lovely.
the location of the first man-powered flight in the UK here at Farnborough.
Yeah.
So I hope you enjoy that, and it takes pride and place on your making.
Certainly will. Thank you very much.
Thanks very much again.
And thank you all for listening.